Hello, everyone. As you're aware of, as the coronavirus spread, we're moving everything online. So today is going to be the first day we're going to record our lectures. And I will upload the lectures periodically every week, and you should be able to see them from YouTube, my channels. And regardless, I will send you the updated link every time I record lectures. So sit tight. We talked about irregular sections last time, and we will complete that section with a whole recording, kind of overlapping what we have talked about last time. But today, let's skip a little bit ahead and talk about the T-beam analysis. Okay, so first of all, let's go over some learning objectives. Okay, so learning objectives. Okay, so we will be able to determine the effective beam width BE. Okay, so quickly recall if you forgot, this is the T-beam. We're looking at basically a floor or slab and with a beam. Okay, so essentially we're trying to determine the effective flange width. Okay, effective flange width. Okay, then to conduct beam analysis. All right, so this is what we're talking about. Come back to black. And then second is to be able to design a T-beam. Design a T-beam with known dimensions. Okay, so this is what we're going to do today. Okay, so with that, let's take a look at the T-beam analysis. All right, so I have a T-beam analysis example to show you here. And first of all, this is to determine the tensile reinforcement. The tensile reinforcement required at midspan to resist a positive moment of 533 cubic feet. Okay, so this is the problem here. All right, so let's take a look. So I have a section like this. It's continuous, and then I have a small lip going on like that. Okay, it's a little bit too long. Okay, and supposedly I have reinforcement at here, bottom of the beam. And why? Because we have positive moment, right? Because we have positive moment. And I know that the depth of the beam D is equal to a 20 inch. All right, and I know my flange here is about 3 inches. Now this is drawn a little bit out of proportion, but you get the drift, right? And then the rest of the height, which is actually the beam and bottom here, is 20 inches, and the width of the beam is 11 inches. Okay, and some information given is that the span is 24 feet. Most of you know that this is basically LN. And the yield strength for the rebar is 60 KSI, grade 60 rebar, and concrete strength is 3 KSI. Okay, so first of all, let's talk about the width. Okay, so to find the width, right? So when you use the equation from ACI, so find BE, and per ACI, BE equal to a lesser of the following equations. First, BW, which is actually this fellow here. Okay, this is BW. Okay, plus a 36 divided by 2 plus a 36 divided by 2. Okay, and then I have BW plus 2 times 8HF. 8HF. Okay, so last but not least equal to Ln divided by 4. Ln divided by 4. So from top, I have here 11 inches plus 36 inches and gives me 47 inches. In the middle, I have 59 inches. Okay, so to break it down for you, this is 11 plus 16 multiplied by 3. Okay, so this is 59 inches. And the last but not the least is the span length, which is 24 feet multiplied by 12 inch per foot divided by 4. And this gives you 72 inches. Now among the three, of course, right? The lesser of the least is this 47 inches of governance. Okay, so governance. Okay, now if this is the case, then I can draw my effective flange width right here to be a 47 inches. Okay, 47 inches. So let me switch back. BE here equal to 47 inches. All right, so pretty simple, right? Now continue. All right, since I don't have the board, so every time I draw a line, so this is border. Okay, this is border. So if I want to say slides, this would be slide number 1, slide number 2, slide number 4, etc., etc. Okay, so with that, I can find out the AS. So this is known cross section. Okay, and to determine AS. And to re-elaborate, don't forget, this is actually the section we're going to analyze, and has a flange width of 3 inches, beam height of 20 inches, and the depth of the reinforcement is 20 inches as well. And the flange width here, B or BF, flange, is actually 47 inches. And the width of the beam, BW here, is 11 inches. Okay, so this is the problem, right? This is the problem. So following the analysis, to determine the reinforcement, we need to have the reduced normal fracture resistance, Mn, Vmn bigger than Mu, right? So assume tension controlled. That means phi equal to 0.9, okay? Then we need to find out our AS required. So AS required essentially equal to Mu divided by phi Fy d minus A divided by 2. D minus A divided by 2. So this gives me Mu divided by phi Fy. For most of you, this is basically what? JD. Okay, and I know that JD for regular beam is what? So recall, put a star here, star. So recall JD equal to 0.9 for rectangular beam. Okay, so I'm gonna put a square here. Okay, so difference, recall difference for T-beam, JD is a little bit different. JD is actually equal to 0.95 D. Sorry, this is D. 0.95 D. So why is deeper? Just because I have what? I have less of compressive zone. Less compressive zone A compared to regular beam. Okay, so now we know that this is approximately 95% of the depth D. So be careful, okay? This is a bit different. All right, so once that is set, I can bring the number into the equation. So AS required equal to 533 cube feet multiplied by 12 inch per foot divided by a 0.9 strength reduction factor assumed, by the way, 60 KSI, 0.95, and 20 inches. This is D, by the way. Okay, so I run the number, I got 6.25 inch squared. 6.25 inch squared. Okay, so this is our analysis. This is our analysis. Okay, so but now I need to actually find out A equal to what? AS Fy divided by 0.85 F prime C. B. Okay, so what is this number now? Should we say BW or BE? So for now, let's assume our compressive zone is smaller than HF. Okay, so now if this is the case, I'm gonna assume this is BE. Okay, so I'm gonna assume this is BE. Okay. Okay, let me get a smaller data points. All right, so this is basically BE. This is BE. Okay, so we have now A equal to a 3.212 inch. All right, so here's a problem. As you can see, this is actually bigger than HF. Bigger than HF. Now, this means we cannot use BE. So basically saying this is invalid. Okay, now with that, this is invalid, we're going to say alternatively, since A is bigger than HF, then need to design T-beam. Design T-beam. Okay, so how to do that? How to do that? This is slide number 4. How to do that? Okay, now remember we said we're going to assume the compressive zone size have two components. One is this part, and the other is the wet part. Okay, and this will give us the equivalent. Compressive zone size. So be careful. This is A, and this is HF. Right? So that was the deal about design. That was the deal about T-beam design. Right? So now what we have to do is let's set a SF. Okay, this is for flange, and this is for web. Okay, so ASF multiplied by FY. Okay, so this is T-beam. Okay, equal to 0.85 F prime C BE minus BW multiplied by HF. Okay, multiplied by HF. All right, so this is about the flange part. Okay, this is the flange part. So from here, I know that ASF from the flange should equal to, before that, okay, let me just try to just move down a little bit. Okay, it's removed. Okay, I'm gonna fix this real quick. So this is flange. Okay, so I'm going to allocate some reinforcement, okay, to equal to the compression force from the flange, right? So from this, ASF equal to a 0.85 F prime C BE minus BW multiplied by HF divided by FY. And that equal to a 0.85 concrete 3 KSI 47 inches BE minus 11 inches BW and multiply by 3, which is HF, divided by 60, which is the tensile strength of the yield strength of the steel, and I get a 4.59 inch squared. 4.59 inch squared. Okay, so from here, I know my moment resistance from flange, Mn, flange, should equal to ASF Fy D minus HF divided by 2. HF divided by 2. Okay, so don't forget, we're still talking about the flange here. So I have 4.59 inch squared multiplied by 60 KSI multiplied by 20 minus 3 inch divided by 2. All right, so this is 424.6 kip feet. Okay, and then I got Mn flange equal to 424.6 kips feet. Okay, so now I need to have my web as well. So my web or phi Mn web, okay, phi Mn web required should equal to phi Mu minus phi Mn flange. Sorry, no phi here. Mu minus phi Mn flange. Phi Mn flange. Okay, now let's just say now I have, right? Now I have phi Mn web equal to Mu is 533 kip feet multiplied by phi Mn, so 0.9, assumed phi 0.9 multiplied by 424.6 kip feet of flange. Okay, and then I get phi Mn web required should equal to a 150.9 kip feet. Very small, very small. Okay, so this is what is required from the web. What is required from web. Okay, now quickly, slide number 5. Quickly recall, right? We're talking about the T-beam, and now we are only interested to see what is a flange, what is a web, right? What is compressive zone of the web? What is the compressive zone of the web? Right? So now, recall, for a rectangular beam, JD equal to what? JD equal to a 0.9D. Okay? JD equal to 0.9D. So, in this case, I have phi Mn web equal to a 150.9 kip feet equal to a AS web, which is reinforcement, balance the compression force from the web, multiplied by Fy and D minus half A. But now I don't know D minus half A, right? So I'm going to approximate this one equal to 0.9 D or JD. Okay, so AS web, oh sorry, wrong color. AS web equal to a phi Mn web divided by Fy JD. Okay, Fy JD. So I bring in a number. This is basically 150.9 divided by 60 KSI multiplied by JD is 0.920 inches. 0.920 inches. So I got a 1.86 inch squared. 0.86 inch squared. Okay. Now with this reinforcement, right, I now go back and check the actual compressive zone size A, and A equal to ASW Fy divided by 0.85 F prime C BW. So this is 1.86 inch squared multiplied by 60 KSI divided by 5%, 0.85, and 3 KSI and 11 inches. I have now a 4 inch of compressive zone. 4 inch of compressive zone. So now let's say the total required reinforcement AS should equal to AS flange plus AS web. So bring the number in, 4.59 inch squared plus 1.86 inch squared. I have a 6.45 inch squared. Inch squared. Okay. So now what do I do? I need to select my bars. All right. I need to select my bars. So this is relatively large area. So one row, one layer of reinforcement is not sufficient. Okay, so I'm going to select 3 number 10 bars plus 3 number 9 bars. All right, and if I do that, my provided steel, switch color back, so my provided steel equal to 6.81 inch squared, which is bigger, this is a pad issue, okay, which is bigger than the required, equal to a 6.45 inch squared. So I'm covered. Okay, so now my section becomes my section becomes 47 inches of flange, 20 inches of D, and group of bar, I have 3 number 9 and 3 number 10 at the bottom. Okay, then you can basically check details. Basically, it's bar spacing. Okay, so with that, we're finished with the T-beam analysis example. Okay, so thank you for watching, and we'll upload the irregular beam design again very quick shortly. Okay, I will send you an email regarding the office hour tomorrow, and I look forward to talk to you then. Okay, thank you very much.